Hello, everyone. Today I'll be speaking about the RE model structure, aka the constructive version of the classical concurrent model structure. Right? So here's the plan. So yeah, I'd like to begin with some giving a brief historical background, like why did we have just talking briefly about why did we need a constructive version of the classical model structure that we had, and then some preliminary things, and then I'll give a description of the model structure via the X infinity functor. Right. So yeah, let me start by talking about constructive mathematics. So what do you mean? Oh yeah, what does constructive mathematics mean? So when I say constructive, it is like the things that should come in your mind. The first thing would be the principle of excluded middle. So the thing is that, so when I say constructive mathematics, that is mathematics that is done without principle of excluded middle or other principles that imply, like, right, like in order to get the gist of it, it's like we are not allowed to use methods like proof by contradiction, just to get the gist. That's what I mean. Now, right. So why do we care about the constructive? So the biggest, so the biggest thing is that, so the classical concurrent model structure, as we know, so it's a kind of an inspiration for Vygotsky's univalent foundations program and homotopy type. Right? So that's one of the places where the inspiration comes from. So we want a constructive version as the most important thing. So maybe I should write this because it's so fundamental. So why do we need a constructive? So yeah, this is one of the most important factors. So we want a constructive version as the law of excluded middle. So let me abbreviate it to LEM. This is the law of excluded middle. And okay, also the axiom of choice. So yeah, AOC is the axiom of choice, are not generally valid in the internal logic of a Grothendieck topos. So let me abbreviate it. Grothendieck topos. Okay. So yeah, maybe let me think about it. So for people who are not familiar, let me talk about what I mean by internal logic. So when I say internal logic, it is like let me think about it for a moment. Okay. All right. So yeah, suppose we have a category. So suppose I'm talking about internal logic right now. So suppose the internal logic, we say that it is induced by a category. So suppose it is induced by a category. So suppose the internal logic is induced by a category C, right? Then what do we mean by that? Then thing is that, yeah, so then the objects of the category C, so objects of, or maybe X, objects of C, X are collections of things of type X. So this is a very rough very rough description. So yeah, I don't need to be complete. So this is just to give an idea. So type X, and then morphisms. So let me call it from X to Y. Are terms. So I see it. So I see it as terms of type Y in context. Right. And then, yeah, then you have a notion of a sub-object. So, okay, that's the most important one. So maybe I should write this. Sub-object. So let me get on to this. Is a proposition. And the logical operations, so yeah, maybe let's start. The logical operations are like, so there are implications by universal, they're implementations by universal constructions as sub-objects. Right? So that is, and so on, and a few other details as well. So this is the basic idea. This is what I mean when I say C gives us the internal logic of some theory, right? Okay. So I hope I don't need to talk about, I don't need to introduce a Gutenberg purpose, but if somebody wants, I can maybe talk about it. So Simon Henry in 2019 established a constructive counterpart of this classical concurrent model structure that we have. So which is what this talk would be about. So yeah, I call it the Henry model structure. So yeah, so why is it really neat? It's neat because it coincides with the classical model structure when you assume the law of excluded middle and axiom of choice again. So that's the reason it's so that is the reason it is more of a generalization. Right? So in the present talk, I'll be talking about so currently we have so after the work of Henri, there was also contemporary work. By and by Gambino and Shunilo, right? On giving different proofs of establishing the model structure. So I'll be talking about one of their proofs, not Henri's proofs, but instead of Henri's proofs, I'll be talking about one of them. They in the paper they give two proofs, so I'll be talking about one, and this is mostly based on that. Right. So yeah, let me begin with the classical concurrent model structure. So the category of simplicial sets. So this is my notation for the category of simplicial sets as a proper Cartesian model structure. So this is something that I hope everybody is familiar with. So we have three distinguished class of morphisms, where W, that is the class of weak equivalences, is the weak homotopy equivalences. And the distinguished class of fibrations, which I denote by this, are time fibrations. And the distinguished class of cofibrations, which I denote as follows, are monomorphisms. Right. So yeah, so let's start from the preliminaries. So yeah, I'll first define a decidable inclusion. So yeah, feel free to point out something if I mess something up. See, I don't have proper notes. So this is maybe a warning. So if there's a mistake that you see that I'm committing, please feel free to point out. So definition, a map. So let me call it from X to Y is a decidable inclusion if there exists a map. So say J, so this map will be called its complement from Z to Y, such that I and J, such that I and J exhibit exhibit Y. So this is Y. So they exhibit Y as a co-product of X and Z. So maybe I'll write that. So I right. So yeah, J is called the complement. Okay, now I define maps called split surjections, which I can pretty sure some people will be familiar with. So split surjection. So it's just a function admitting a section, right? As simple as that. So it's just a function that admits a section. So, right. So now maybe a remark. So assuming the law of exploded middle, every injection is a desirable inclusion. And every surjection is split. Right? Okay. So now I'd like to define Van Kampen colimits. So let me start. So yeah, first define. So maybe I should start by defining universal and okay, so I'll go that way. So suppose we have a category. So let C be a category with finite limits. Hope my writing is not completely like illegible. If it is, please feel free to point out. So yeah, so we consider a diagram. Right. So yeah, so the colimit colimit is said to be universal if for every morphism, for all morphisms, from another colimit, it should have following right? Okay. And it is effective if for all Cartesian transformations. So yeah, let me keep it B. The colimit of B, sorry, of B exists, and you have the following points. Already, right? And it is said to be Van Kampen when it's both universal and effective, right? Right. Sure. Okay. Okay. So yeah. So let me talk about a few things. I think these you can also find these on the paper. So a few definitions related to Van Kampen colimits. So some important terms that you should know. So we can X is a category with pullbacks. then X is said to be extensive get rid of this. Is extensive if coproducts exist and are vacant. Right. And then so we like this. X is okay. So let me excuse me for a moment. Stop for a moment. Yeah. So okay. Now I'm decently hydrated. So X is said to be adhesive if pushouts along the monomorphisms exist and are all Van Campens here. And are Van Campen. So there's another term. So X is said to be omega exhaustive. Wait. Yeah, I think that's right. It's easy to get mixed up with the term now. If sequences of monos that form, so yeah, that's where the omega comes from, that form an omega index diagram in our category X have co-limits that are Van Campel. Right. So yeah, so an elementary fact, and yeah, so maybe I'll state it as a lemma, and I won't give a proof. So it's not that difficult. So the category of sets, so this is my category of sets, is extensive. And we'll see that we'll use this result to prove similar results for the category of simplicial sets, right? Because everything works pointwise, right? So yeah, so it's one of the cool things that you can do. And it's adhesive and omega. So all the things. Right. So another important lemma. Okay. So again, yeah. So then I won't spend a lot of time giving proofs of all the things. So I'll just state this, and in some cases I'll just talk about, maybe give a sketch, and in some cases I'll give a proof. So yeah, in the category of sets, so this is again very important, and we can prove this. All desirable inclusions are monos. Yeah, this is very important. We'll be using this later. And all desirable inclusions are closed under pullbacks along arbitrary functions. So can all undesirable inclusions closed under retracts. Right. So yeah, maybe a hint would be that in order to prove that, you just need to use the fact that the category of sets is extensive. You just need that and prove it. Okay. So an important proposition. So now, yeah, so this kind of So this kind of, we'll realize that this kind of is the basis of the Henri model structure. This is very important. So desirable inclusions and split surjections. So yeah, they form a weak factorization system. Form a weak factorization system. Right. So let me see. Let me think. So yeah, okay, let me give a proof of this. So yeah, it may not be completely a proof, but this should do. So we say that for any morphism. So you take a morphism, so suppose this is our morphism. So you have a factorization of this form. So let me call this G and H, where G is, so G is a desirable inclusion by construction, you can check this. So the way we have constructed it, G is a desirable inclusion. And and H is a split surjection. So you can see that because and H has a section because of this inclusion pattern. So okay, so yeah, let me make sure that I don't mess up the notation. So so that puts it. And yeah, the lifting properties are immediate, so you can see that. Okay. So now, right. So maybe a remark. Okay, let me. I was thinking whether I should talk about this or not. So maybe a remark. Or okay, maybe I'll just say this. So the sub-objects corresponding to desirable inclusion, right, which are monomorphisms as we knew it, are called. Right, so I think it's worth writing instead of just talking about it. So okay, let me write this as a definition. Sorry. Okay, so sub-objects corresponding to desirable inclusions, which are monomorphisms, right? Called we call so Gambino, Sattler, and Shumilo call them desirable subsets. Right. So a fact would be the, again, I want to give a proof. So desirable subsets are closed under finite limits. Right, so it's just a fact. Okay. So, okay. Let me think about it. If right, so yeah. Okay, I think that's enough. So now, okay, so now let me kind of give a quick recap about simplicial sets and weak factorization systems. So I don't know. So let me use a different ink then. So this is let me write the title. So maybe a recap about simplicial sets and weak factorization systems. So yeah, so for me, it's like I denote the category of synthesis with the bold delta, and the standard synthesis are other elements by lighter tone, but here I'll use a different color. So this is a category of simplices. What is that? So this is like the category of AKA the category of finite ordinals. Right. And order preserving maps. Right. So let me fix the notation for the standard simplex, because there are different notations that you find in the literature. So my standard simplex, I denote my standard simplex. Standard and simplex. This is the way I denote it. So yeah, this is just a pre-sheaf. So this is the way to think about it. Pre-sheaf on the category of syntheses. Presented. Okay, so now let me give a definition. So the category, so the pre-sheaf category of the category of syntheses, that is pre-sheaf category. Sorry, I denote this by this. So this is manifestation. Where is the category of simplicial sets? So now, let me define the cophase and co-degeneracy maps. So define them. So this is my face maps. Okay. And square them equal to 1. And so let me check that I've not missed the notation. Yeah, seems to be fine. So yeah, so this is kind of obvious, but let me write this. So the cophase plan is the unique injective map. So this is what I mean, the injective map without I in its image. And the co-degeneracy map. So there is a unique surjective map. So that takes the value of I twice. Right. And so it's easy to verify that for all morphisms. So for all morphisms, so let me. Okay, let me just try to. So for all morphisms, so you can easily verify this. For all morphisms in a category of syntheses, there exists unique factorization into a composition of cophase and a co-degeneracy map. Cophase and a co-degeneracy map. Right. So yeah, so again, let me fix my notation again. So for the phase and the degeneracy maps. So yeah, so this my notation. So in case you're wondering the notation, so I'm using Szyszynski's notation. So this is the notation that you find in Szyszynski. So this is the notation that I will be using. So okay, so theorem. So now, yeah, so as I said, so now I'll use the fact that I just kind of made a statement that that I said was easy to prove. So we'll see that we'll use that to prove something further. So the category of simplicial sets is extensive, adhesive, and exhaustive. Right. So there's a one-line proof. So this is, so I don't know. Should you write that as a proof? So it doesn't seem like one. So proof is right. So it is immediate as monos, homomorphisms, fullbacks, and full limits of presentable elements are determined point. Right. This is what I was saying. Right. And so yeah, and then we use the fact, yeah, so maybe this is a really tough sketch. I don't want to call it a so yeah, so you just see that. And then you use the fact that the category of sets is exhaustive with these omega exhaustive with these index. So it's everything's one place. So now, okay. So now let me, so yeah, so again, I think if I remember correctly, this is also the notation that this is also a notation in Gambino satellite Chomillas paper. So because these are important, so let me denote these inclusions. So maybe a notation. So denote this by as from I1. Right? This is the notation. So again, maybe a remark that that's quite easy to see. So just for completeness, I think so the category of simplicial sets. So this is the interval object. Just because I feel it's worth writing. We're not going to. So yeah, maybe a recap of so let me pause and think if it's worth talking about these again. Okay, so let me go ahead and again. So talk about some recap again. So yeah, recap of stuff that we already have. So that yeah, so stuff that Drisha has talked about in the previous talks. So again, so let me just remind that to you. So the cylinder again, these are really elementary facts. The cylinder on simplicial set. Sorry for my inconsistent notation. So it is supposed to be a lowercase s for right. So it is the product. So this is my formula. This is the way I see it. So this is my definition. And then if and F are morphisms, so from say X to Y, are morphisms in the category of simplicial sets, and then right. So there exists a map. So I'm talking about. So yeah, this is the definition of homotopy. So this is a map. So yeah, so this is a homotopy is a map such that. So let me denote this by H. So I'm using my notation, so we'll see why. So this is more useful. It's more useful to write it like this. So, right. So we denote the fact that F and F dash are homotopy. Standard notation. Okay. So again, yeah, let me mention this as well. So the constant homotopy on a homotopy F is the composite. So it is the composite map F pi, where pi is just projection. So some basic things so far. And now let me briefly write, give the definition of homotypic equivalence. So map is a homotypic equivalence. There exists not a map of the policy such that is homotypic to identity of A. Right? And she is homotypic to identity. Right? Okay. So now an important fact. So so yeah, again, this is some notations. So we know that for n greater than or equal to 0, and so we have Horn equations. So, right. So I'll call my set of Horn inclusions by J. Right. And similarly, we have a boundary inclusions. And I will be my set of boundary inclusions. Right. So, okay, so now let me define trivial vibrations. So maps with right lifting property. So this is my acronym for right lifting property with respect to I are called trivial vibrations. So we'll see that trivial vibrations coincide with basically vibrations. But let me define trivial vibrations like this. Okay, are called trivial vibrations. Okay. And yeah, so co-vibrations, it's easy to see what co-vibrations have the left lifting property, which is trivial vibrations. So, okay. So now let me define a configuration. So, so this is a configuration. If it has, again, sorry, yeah, it has the right lifting property with respect to J. So I think I'm going to draw this. Although I don't need to draw that. So another definition. So maps with the left lifting property with respect to configurations are called trivial vibrations. Trivial co-vibrations. And okay, I don't want to write definitions so many times. Okay, a simplest was just a non-complex. Okay. So okay, let me call it 6. So that's a configuration. Right. So okay, let me define cell complexes also. So, okay. Again, a definition again. So for a class of morphisms of a category C, for some category C, or K cell complex, so let me underline K cell complex of I say n, that's not equal to omega, is implicit, is n composition of push-outs of co-products of maps. Okay, right. So this is my definition of a case in cell complex. Okay, so again, a lemma for which I want to give a proof. So we can prove that every trivial vibration is a vibration, and that every trivial co-vibration is a co-vibration. So okay. So yeah, maybe I'll just. So instead of giving a proof, maybe I'll just talk about. Maybe I'll just give a sketch. So you'll realize that it suffices to check that every Horn inclusion is, and you'll realize that every Horn inclusion is in fact an I cell complex. So the way I've defined I to be a set of boundary inclusions. So you just need to use the fact. So let me write this. Use the fact that. So you can just you can prove it as follows that Horn inclusions or Horn inclusion is an I cell complex of height 2. Okay. So yeah, now I define a weak factorization system. So weak factorization system in category C is a couple of classes, so let me call them X and Y, of morphisms such that, so again, you can find the definition Susinski, such that X and Y are stable under retract. So what do I mean by that? So maybe let me just draw it icon so that. So okay, so jobs. So let me name this G and let me name this F. So F is a retract of G, and this is equal to the identity of X. This composition right here, this will be the identity of Y. Right. So when stability under retracts means that if G is under X or G is G is in X or G is in Y. So is F. So this is what I mean by stability under retracts. And X is equals to L of Y. So L of Y is equal to the so this is equal to the class of morphisms that have left-lifting property with respect to Y. Okay, so yeah, I think that's understood. Now I don't need to see writing this. So okay, right, and Y is equals to Rx, where R is defined vice versa. There is maps having right-lifting property. Right. And the third and most important, probably the most important condition is that. So you have a factorization. So any morphism in the category, so let me go H as a factorization. H is equals to GF, where F is an X and G is right. So this is my definition of a weak factorization system. So okay, now let me state some important results, and so maybe I won't prove all of them. Yeah, so I won't prove the first one, but I will see. We'll see how it goes. So two important lemmas. Okay. All right. So okay. So these co-5. And in fact, so let me also add this. It's important. The boundary. So it's a cell complex with respect to. Right. So, okay. So now another important lemma, that is some sort of a cancellation proposition. Cancellation kind of a lemma of trivial vibrations. So cancellation property. So okay, F and G are morphisms in the category of simplicial sets, and F and GF are trivial vibrations, then so is F, so is G. So let me see. Maybe let me try and prove this. Okay. Okay, let me try and draw this first. Right. So yeah, this is our lifting problem that we have. Okay. Yeah, so this is like, yeah, we know that this is a cofiber from the previous lemma. So that is because, yeah, so because from the previous lemma we know that this this thing, so this is a cofibrant object. So we see the fact that it is a trivial fibration. G is a trivial fibration has this lifting problem. And now, okay, yeah, right. So now again we use the fact that delta, right? So yeah, the boundary of the boundary is a cofibration of the previous lemma. So we use that to, I think we can do this. Yeah. So first, let me. Okay, I'm sorry. I think maybe I should have talked about this before. So let me say the way. Yeah. So almost half away. Let me say the way I'm decorating my arrows. So this is my. So this denotes a cofibration, and this denotes a vibration. The squiggly. So this is a trivial vibration. This squiggly is a trivial cofibration. And so yeah, so I am intentionally distinguishing between acyclic and trivial cofiberations. So yeah, we have different I'll have different notations for the arrows. So this is my acyclic cofibration. Right. So again, so yeah, so we'll use the fact that that this is cofibrant, so we can have. So let me call this yes. Then so yeah, so from this we can get an equivalent lifting problem, which so I think I'm going for it. So hope I don't miss. Get this lifting problem. Think. Yeah, right. So yeah, so this will be GF, right? So from A to B is F, this is G. So this will be GF, right? So yeah, because DF is a trivial cofibration, so yeah, we have a filler, we have a diagonal. So let me call this the blue tilde. So yeah, so from this, so to our original lifting problem, we'll get a solution. Right. Proves it. So yeah, I hope this is right. Okay. Okay. And other things you can, yeah, sure. So yeah, so now I'll talk about some. So yeah, so the push out product properties. So let me properties. So yeah, it will be really brief because of the time frame that I have. After, so yeah, these are our weak factorization systems. So we know. So, so yeah, these are the weak factors. So this is a distinguished class of cofibrations. This is a distinguished class of trivial cofibrations. So this is notation. Right. So yeah, maybe some notation, important notation. So for a simplicial set, let me call it M. So let me take objects in the slice category for these objects in the slice category. So, yeah, so the exponential, so I denote the exponential object as follows. Exponential object in exponential category. Again, a few more things. So let me define the push out product and the pullback exponential. So for the there's, let me see. So this is and so let me call this Q. A to B. We have. So can I hope I don't mess it up? So don't trust me very much. Right. So this is push out. That's fine. And so this is pullback exponential. So I have J and Q. Okay. Right. So this is a pullback exponential. So let me push out order. Pullback exponential. Okay. So let me state this proposition. So yeah, I will give a proof. Or yeah, maybe let's see. So M is a simplicial set, and right. So okay. So if we have okay. So we have so yeah, these are cofibrations. And let me name this I. Let me name the other one J. Cofibration. Sorry, let me write this completely on cofibrations. Let's get it. And so is the push on product. I want to prove this again, as I said. So if again, let me, but okay, so next one, JB is a cofibration. The so this is a trivial fibration. There's trivial observation in this. And then the pullback exponential is trivial observation. Right. So let me see. So yeah, okay, I want, yeah, so maybe, okay, let me give a sketch. So for one, so yeah, it suffices to verify that, yeah. So for one, it suffices to verify that for simplicity. So again, dash. So yeah, so we know that, right? So the push out product is a configuration. Push out product of functions is a configuration. Okay, so we need a filtration now. Give me a moment. Okay, so yeah, you can prove two from one by a joint, by a jointness. But yeah, let me give a proof of one. Okay, so we have a filtration, so we can try and we have a filtration. Yeah, I don't remember this. Yeah, I have notes for this. I have written this. It's not easy to. So the last one, okay. Maybe look at this properly. Sorry. So this is just equal to. Right. So yeah, where is x numbers? Yeah, so it is found iteratively by taking push outs as follows. So yeah, so first let me define this. So okay, let me define this first. And one of these maps is surjective, and this is an injector, right? So this is my case, and you take push outs of the following form. Wait, sorry. Right. So yeah, that way you can prove it, and 2 follows by joint consequence. So yeah, so now let me write a few important corollaries. So right, so if you take a simplicial morphism or a morphism in simplicial sets, and A is cofibrant, then right, so then this is functor, slice categories, preserves cofibrations. So again, I want to give a proof. Okay, I can use the previous theorem to do this. Or let me reconsider. Okay, yeah, I want to prove. So, okay, a proposition. So, yeah, again, this is an important one. So, okay, so let me call it one. You have a trivial cofibration. There's trivial cofibration, and you have a just a cofibration. Then this is a trivial. So let me call this A, this B. So yeah, let me club on for the fence. Okay, so if you take a cofibration and another confibration, and then the pullback exponential, also the way we define it, is a confibration. And another one, C, is the last. So you take a trivial cofibration and confibration again. Then there again the pullback exponential is trivial confibration. So yeah, maybe let me refer. Okay, so for A's proof can be found in Gabriel Zisman's book Calculus of Fractions. Right. So yeah, you can find the book in Gabriel Zisman. And I think if I remember correctly, even in if I remember correctly, even in the paper, Gambino, Sattler, and Schuler's paper, they do the same. They refer the reader to the Gabriel and Zisman's book proof here. And right, so yeah, and then B and C will follow by joint means. Joint means. Okay, now comes the important section. So of really desirable inclusions. So yeah, what is the goal? So let me write this out and spell it loud before. So we want to show that, so yeah, this weak factorization system that we saw coincides with the weak factorization that is formed by desirable inclusions and split surjections. So this is the goal. So, okay, let me define a really desirable inclusion real quick. So, map. So let me this one. and the simplicial search is going to desirable inclusion if for all and the following is a desirable inclusion. So yeah, this is the latching object that Risha talked about in one of the previous talks. So yeah, this is desirable inclusion. So yeah, dually, so homomorphism again become X to Y in a simplicial search is a 3D split surjection if for all M the following is a split surjection. And here, this is the matching object. Right. So this is what I mean. So a lemma so I had maybe thought of talking about this a bit later, but we do desirable inclusions coincide with cofibrations. The split surjections coincide with triple fibrations. So yeah, or instead of giving proof, let me talk about, let me just give an idea. So yeah, just the idea is just the fact. So yeah, right. So we know that. So yeah, we just use the fact that desirable inclusions, the class of desirable inclusions, and the class of split surjections from a weak factorization system, right? And in fact, that I think that I didn't talk about is that the weak factor. So it is also, so the generation is cofibril. Right? So if we consider the factor, so if we consider the pair of classes of reedy desirable inclusions and reedy split surjections, so its cofibrin generation with right. So it is also right. So I don't know if I should write. Anyways, so its cofibrin generation will be a weak factorization system. So I mean, I don't want to get into the details. So okay, yeah, you can. Okay, let me refer this to there's a paper, Real Verities paper on reading. Okay, let me just write the initials, but I don't remember the title of the paper. So yeah, maybe I'll later update that in my notes. So okay, let me move forward. So maybe a remark or no, not just a remark, but okay. For okay, let's consider a simplicial set. Every degenerate operator acts. So yeah, I won't give a proof of this. Acts by monomorphism. Oh, I'm sorry. So we are in other way. Anyway, so 2046. The latching map is a mono. Apart from that, so okay, so let mono in category of simplicial sets. Then for every degeneracy operator for set the n is the intersection of subobjects of subobjects Qn of Qm. Fourth, so this is the intersection of subobjects and Q. Right. So yeah, I'll give a proof. So lemma. So let's take a couple of really desirable inclusions. So if for x from y to z and say d to w, dt desirable inclusions of simplicial and co-simplicial sets, then this is an important lemma. Let me write it down first. Right. Oh. Okay, so now let me pause for a second now. Think about this. Right. Yeah, so it goes. Oh, wait, sorry. There's a desirable. Right, so this is my lemma. So now we talk about the characterization of the cofabrications in the Henri model structure. So maybe a proposition. So the following are equivalent. So this is a cofabulation. So desirable inclusion and for each generating degeneracy operators the map, this map, so this would be a desirable inclusion. And the other one that, yeah, so you'll see that the other one is more generalized, kind of follows from this one. It's because these are the generating degeneracy operators. So is a desirable inclusion. So the third one is so if this is a, so if it is a level wise, meaning in all the levels, desirable inclusion, and for each degeneracy operator, so from end to end, the following map is a desirable inclusion. Is a desirable inclusion. Right. So yeah, proof. So its proof is a bit involved, so I won't get into it. But so yeah, maybe I'll show you how you can So yeah, I won't show you how you can move from 1 to 2 or from 3 to 1. So I'll show you how you can move from 2 to 3. How you can put the 2 plus 3. So right. So every degeneracy operator, say, so it is a finite composition of generating ones, right? So then, this, this is what I talked about. A finite composition of push-outs of maps. Right, so this comes from the second. For and hence is a desirable. So now, okay, let me write this down. So for all, and we have the factorization. Let me write this continuation. So we have a following factorization. Yeah, so this map is just a push out. So yeah, we use this. So and so yeah, we can show that, and because of that, it's decided. Yeah, I won't get into the details. So yeah, so again, some important corollaries that I'll write. I'll just write. So the simplicial set is said to be cofactorial if all generating degeneracy operators act on it by desirable intelligence. Can't give a proof. So another corollary, first point is every cofibration is a level-wise desirable inclusion. A level-wise desirable inclusion with the cofibrant codomain, the cofibration. Right. And your proof. So okay, let's move on. So we got lemma. So if we consider a mono and y is cofibrant, then so is x. Okay. So okay, I think let me give a proof. So yeah, let's consider. So suppose this is a degeneracy operator. So yeah, then by the previous corollaries, so yeah, this is also using previous corollaries. Like one of the previous corollaries. But I don't want to specify all the time that whether it is the corollary just preceding it or the one before that. So I would just say using some previous corollary. So it is also a desirable inclusion. Right. Again, yeah. So again by one of the previous results. So this is a pullback. And is thus a desirable inclusion. Right. So again, now using the previous lemma, we can, using the previous lemma, we can write this out. The cofibrancy. Okay, so now let's prove that. So now let's prove the closure of cofibrant objects under right with respect to exponentials, right? So yeah, let me write it. Exponential. So on math, in simplicial sense, is a generalized. So yeah, for that I define the notion of a generalized degeneracy. Generalized degeneracy if for all cofibrant set A, the map is a decidable inclusion. So lemma, so the class of generalized degeneracies contain the degeneracy operator and is closed under composites, finite polymerage, and push outs along arbitrary names and also retracts. Right, so yeah, I will give a proof. I mean, yeah, I won't give a proof because we don't need a proof anymore, it's immediate. So yeah, again, using one of the previous results, again, I won't specify which one. So yeah, so immediate. Okay, let me just write it. Immediate as sorry. Almost, I see that I'm almost out of time. Still have a lot. Quick. So immediate as immediate as degeneracy operators are generalized degeneracies. So you can just prove it using our. So now a lemma, if a simplicial set X is a finite colimit of representables, and then there's a generalized degeneracy. So let me ask, I mean, is it all right if I take an additional 15 to 20 minutes? If not, then I'll have to rush a bit. So is it okay for me to take an additional 15, 20 minutes?
Yeah, sure, of course.
Thanks. So okay. So let me sketch a proof. So yeah, it's recorded anyways. There's a probability to read. So yeah, as a category X is a finite colimit of representables. So again, so we'll use a previous lemma. So yeah, using the previous lemma, we can just reduce it to the case of X is equals to that. Right. So now, okay, now let's look at this. So this is the row wise. Yeah, I'll draw the line. Row wise co-limit of the diagram. So let me draw the line. sorry. So yeah, the unlabeled arrows will be the identity arrows. So right, you have a diagram of this form, something of this kind. Uh, as said, the unlabeled arrows are identity. Yeah, so then the desired result follows from the previous line. So yeah, again, I won't get into this. Okay, so let me define the deformation, or deformation sections. So let me write this out. Deformation, retraction, no, oh my bad, deformation section of a map. So it's another map from Y to wait. Let me pause for a moment. Okay, yeah. Such that f(g) is equal to identity of Y, and there exists a zigzag of fiber-wise homotopies from GF or X. Okay. So a map admitting a deformable section is called shrinkable. So yeah, because of the time, I will skip a lot of the things that I was planning to talk about, that I had in my mind. So, okay, so a lemma. So this map, yeah, this is shrinkable. And let me write this out properly. Right, and a proposition. Okay, so let's consider a map such that B is a cofibrant and pullback of A along maps is a visual maps is a finite colimit of representables. Then this map is a so this map is functor rather preserves cofibrant objects. It's not possible. Right. So yeah, so now let me talk about the fibration category structure that we see. Right. So yeah, we're reaching close. So okay, I have 17 more minutes. So yeah, so we proved that if we have a fibrational simplicial set, then the full subcategory of simplicial sets over M, right? Okay, so let me write this down instead of just. So if M is a vibrational simplicial set, then the full subcategory of simplicial sets over M spanned by vibrant objects admit a, sorry, it's getting worse, vibration structure. Now, what do I mean by a vibration structure? Let me write the definition. So a vibration category C is a category with a subcategory of weak equivalences and a subcategory of vibration such that the following axioms, right? Let me write down the axioms. Such that C has a terminal object. I'll rush through all of them because there are 4 of them. And our objects are vibrant. Right. Pullbacks along vibrations exist and C and cyclic vibrations stable under pullbacks. Right. So yeah, the weak equivalences satisfy the fixed property, and every morphism factorizes as a weak equivalence followed by a average. Right. So now, yeah, let me state the key here. Yeah, I'd like to call this key here. So far, if X is cofibrant, then the category okay, let me see, yeah, I've not defined this. So yeah, so what is this? Sort of write this in the brackets. So this is a full subcategory of so this is the full this is the full subcategory of category of simplicial sets which are spanned by covalent objects. So yeah, I don't think so full subcategory of so yeah, what do I mean by this? So this is the Groton deconstruction of our yeah, so it's a Groton deconstruction. So this is the full subcategory of like Groton deconstruction, or you can call it in some places it's also called a category of elements, right? Full subcategory of this spanned by current vibrations over X. So yeah, then the category is right with fiber-wise homotopy equivalences and current vibrations is a vibrational category with acyclic vibrations being the trivial vibrations, right? So yeah, let me talk about the mole structure. I'll talk about the mole structure via the X infinity functor. So I'll kind of let me define the weak equivalences of the mole structure first, then I'll kind of give a brief kind of an introduction to the X functor. So yeah, for that, first let me define a strong cofibrant replacement. So a strong cofibrant replacement of a category X is a cofibrant simplicial set such that X tilde such that you have this trivial vibration. So yeah, now we have there are 4. So the weak equivalences are the weak homotopy equivalences, and there are 4 cases that we have, right? And we'll see. So a map from X to Y is a weak homotopy equivalence. If so, the first case, so let me call it A1. So X and Y are cofibrant Kahn complexes. So then it's a homotopy equivalence. Right. A2 would be X and Y are just Kahn complexes. Then it has a weak homotopy equivalence. Ah, why? I'm sorry. Then just a Kahn complex. It has a strong cofibrant replacement. That's a weak homotopy equivalence. Right. And our third condition is XY. Cofibrant. So this is a bit different from the other cases. So if this is a weak homotopy equivalence and K is a Kahn complex or a Kahn complex, then you have a weak equivalence. If so arbitrary, this is the most general case. So it has again similar to A2, strong cofibration replacement. That's weak homotopy equivalence. So yeah, so now I'll just state the lemmas. I don't have time for the proof. In the category of Kahn complexes, weak homotopy equivalences satisfy 2 out of 6 property and are closed under the tracks in sense of, so let me write this in brackets, in sense of A2. Definition 2. Every trivial fibration and homotopy equivalence also satisfy A2. Right. So I don't have time to go through the proof, but similarly, in the category of special sets, weak homotopy equivalences satisfy 2 out of 6 property and are closed on the retracts in sense of A4 this time. They are just special sets. And every trivial fibration and homotopy equivalence satisfies. So again, so I'll just state it as a proposition. Map of superficial set between Kahn complexes as an acyclic fibration, Kahn fibration, if it's a trivial fibration. So I don't have proof. I don't have time for the proof. So now, so an important theorem. The category of Kahn complexes with weak homotopy equivalences in sense of A2 and Kahn fibrations is a complete vibration category. Similarly, the category of co-vibrant simplicial sets with weak orthopic equivalences in sense of every and co-vibrations is a co-complete co-vibration. So now let me state an important gluing lemma. We are working in the setup of a co-vibrant category. So we have this cube. Let me try and draw this correctly. Oh, this is not too bad. Wait. Right. So yeah, let me write this. So if top and bottom squares push-ups along two vibrations. Sorry. Whatever way. And the map from are weak equivalences, then so is this map. This map. Right. So yeah, now let me a little bit talk about bisimplicial sets. So a bisimplicial set is a species of so a bisimplicial set is co-vibrant if again this is similar to the previous case. It is co-vibrant over a set that is you again have the notion of a latching object and this map is a desirable inclusion for all Mn, and it's now it's really co-vibrant over simplicials, the category of simplicials. That is, right. So this is a co-vibration in the category of simplicials. So I'll skip the section on the X infinity functors, and maybe I can talk about it some other time. So I'll just assume that we understand the X infinity functor. So first, let me define the skeleton. So the kth skeleton X is the co-end. So again, because I don't have time, I won't. I can't explain most of this. Right. And diagonal is the simplicial set, diagonal of X, right? Oh, wait, I'm sorry. So this is the simplicial set. So I won't. So there are two important things that I kind of have to maybe skip. Now there is so the first is the X infinity functor. So let me write that down. So the X infinity functor equivalence theorem A that I'll use So yeah, so let me just say this. So the X infinity functor preserves, so it preserves finite limits, it preserves confibrations between cofibrant objects, trivial fibrations between cofibrant objects. And if X is cofibrant, then X infinity of X is also cofibrant. In fact, it is a count complex. So, and if X is cofibrant, then the map from X to X infinity of X is a weak homotopy equivalent. So I just, yeah. So I felt it's okay saying, and so we can conclude. So again, the theorems. So a map in simplicial sets is an acyclic vibrations if it's trivial vibration, and it's an acyclic cofibration if it's a trivial cofibration. So yeah, the theorem would be then the cofibrations, the way we have defined it, the cofibrations, so which are the ready desirable inclusions, the confibrations, and weak homotopy equivalences form model structure. So yeah, just give me 2 more minutes just to sketch the proof structure and simplicial sets. So, right. So, okay. And we can also prove that, so the way we have defined it, cofibrations and trivial fibrations. So yeah, these cofibrations are the really desirable inclusions, really complementary inclusions. So these are weak factorization systems. Right, so yeah, we can prove this. So this is supposed to be a sketch, not a complete proof. Also, we can use previous, so yeah, and we have used previously lemmas to prove that acyclic using previous results. Again, I won't specify which. Acyclic fibrations are trivial fibrations, and acyclic cofibrations are trivial cofibrations. So yeah, that kind of proves it. And without taking any more time, I'd like to start. So yeah, maybe you can stop the recording now. So let me stop my screen sharing.